This is a nice, easy topic, which is in the new A-level. It wasn't in the old A-level. And basically, all that we're doing is we are saying if sine is really, really small, so like this is a graph of sine theta, and we're like, oh, down here, really, 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 really tiny, then basically, if you think of a graph, actually I'm going to do it in green so you can see it better. Think of the graph of y equals x, y equals theta rather, since that's my angle, y equals theta, and this is y equals sine theta. Well, for small angles, they're basically the same. So sine theta is more or less the same as theta. And you can see the same thing with tan. I mean, tan's got an asymptote down here. This is y is theta. This is y is tan theta. When we're really, really small, they're basically the same. Now, cos theta, a bit more complicated. The graph that models that really well is this one. And this green one is y equals, well, it's gone up. It's a quadratic upside down, moved up and squashed in. So it's 1 minus a half theta squared. And then the black one there is what cosine theta looks like. So they're really, really similar for tiny values of theta. Okay, now you can see from the graph that for sine theta, the approximation is going to be a tiny bit too big because the line is above the true graph of sine theta. So the approximation is a bit too big for sine. I'll just put it here. Too big. The approximation for cos theta is going to be a bit too small because the green graph is underneath the black graph, the true value. And the approximation for tan theta is going to be a tiny bit too small, because we think that it's this green value and actually it's the black value. And obviously the further you get away from zero, the more this is just absolute nonsense. Near zero, yes. In radians, yes. But if you go bigger or you use degrees, this is just complete nonsense. It's not even true at all. You can do further approximations. So if you use these approximations and you end up with a cubic or even a quadratic, to be honest, then you can ignore the cubic terms, you can ignore the quadratic terms, because if your theta is small, then your theta squared, like 0.001 squared, is like teeny. So always have in your head that theta is really, really small, and remember that theta is in radians. A very common question is percentage error. To work out percentage error, you're doing the true value minus the approximate value over the true value. But what you need to remember here is that percentage error isn't, we don't care whether it's a bit too big or a bit too small. So you would just want sort of the absolute value of that error. So instead of true minus approx, really what you should do is do the big one minus the small one. And you know which one's big and which one's small, because you know that for sine, your approximation is the big one. Whereas for cos and for tan, your true value is the big one and your approximation is a bit too small. So that will mean that you get a positive value for your percentage error. Right, and the bigger your x or the bigger your theta, the worse your error is going to be. Why are we doing this? Well, because we can't always solve equations. And we might be an engineer, or, well, yeah, an engineer. I can't think of anyone else who would want an approximate solution. But we might be an engineer or a business or something like that, and we don't care about the exact detail between these two graphs here. They're similar enough, so we just want to know what it's going to be roughly, like to 5 decimal places or something is fine. Okay. Let's have a look at these two questions. So first of all, find an approximation for sine of pi by 6 plus theta. This is in radians, good. And apparently theta is nice and small, good. So sine of theta is approximately theta. So sine of pi by 6 plus theta is approximately pi by 6 plus theta, right? Wrong. Sine of pi by 6 plus theta is not approximately pi by 6 plus theta, because this is not small. Well, it's not small enough. Okay, if theta's small, then 2 theta small, 3 theta small, multiples of theta and powers of theta are going to be small. But if I add pi by 6 on, it's not small anymore. Okay, so 2 theta, 3 theta, 4 theta, etc. is okay. That will still be small, but not theta plus something. That's not small enough. So what I need to do is use my compound angle, my addition angle formula. here. So if you don't know that yet, don't worry. It's just one of the formulas, one of the many formulas that you're going to learn. So the formula is sine cos, and then the same sign as that, so a plus, and then sine cos. Okay, now sine of pi by 6, menu 1. And we are in radians, and we are doing sine of pi by 6. And I do know sine of pi by 6, actually. It is, actually, do I? No, maybe I don't. Anyway, the point is, I'm not taking any risks. Half, good. So sine of pi by 6 is a half. Now, theta is really, really small, so I can approximate it with 1 minus a half theta squared. Sine theta, I can approximate with just a theta. And then cosine of pi by 6 is going to be root 3 over 2, but I will just check that just in case. Yep. Okay, so sine of pi by 6 plus theta equals this, which is approximately equal to this. And if we tidy that up a little bit, the number at the front is going to be a half. Then we've got add root 3 over 2 theta. That's that term. And then we've got minus a quarter theta squared. Now, this is going to be a good approximation of this when theta is really, really small. And because theta is really, really small, this is going to be really, really small. This is going to be really, 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 really small. So this whole thing is going to be approximately equal to a half. Right, second question. Can we fit it down here? I think we can. Now we're doing percentage error, and we've already done the percentage error, and it's apparently 1%. So I don't know what angle I used, but the error is 1%. Now, I want to do true minus approximate over true, or approximate minus true over true, depending on which one's bigger. This is sine. My approximation is going to be a bit bigger. So what would the approximation for sine theta be? It would be theta. So here's my approximation. Here's my true value, which I know is a little bit smaller. I'm dividing that by my true value, and I'm told it comes out to be 1%, so 0.01. Right, I'm going to multiply this up here. And then I'm going to add that sine theta. Oops, I didn't multiply it. And then I'm going to add that sine theta to the other side. Now, 1.01 is 101 over 100. So all I need to do now is multiply both sides by 100. And I get the result. So the only thing you needed to remember here was that to get my percentage error, I wanted the big one first, and the big one for sine is the approximation. The other question that it's not a question, but it's a thing to just be careful of. I should have put a little cone here really for being careful, but I will attempt to draw one, is that quite often you will get something which has 1 minus cos theta. Or let's embrace two of the common mistakes by putting 2 theta. If you have 1 minus cos 2 theta, the cos 2 theta can be approximated with 1 minus a half, and then it's going to be this thing squared. And you must remember that 2 theta squared and 2 theta squared are not the same. 2 theta squared, that would be wrong. 2 theta, the angle, squared. That's right. But there's this 1 minus at the beginning. And that's what students do wrong. They don't bracket off this, which is all being taken away. And this is a common mistake across all of this stuff where you've got minus 2 things, but here's a very common example of it coming in. You must put those brackets on so that that minus applies to both of those things. And then you've got 1 minus 1 gone. Minus and minus is a plus. And then you've got a half multiplied by 4 theta squared.